We move on to the conservation of momentum principle. This is an important conservation law in physics, like the conservation of energy. It allows us to solve problems. What do we mean by conservation of momentum? Simply, it means that momentum before collision is equal to momentum after collision. Okay? This is the case when you have an isolated system. An isolated system is a system that includes all parties, that includes all colliding objects. Okay? This is what we mean by isolated system. So here you have these two balls colliding. This is an isolated system. The momentum before collision is equal to the momentum after collision. Here you have this collision with this between a proton and a helium nucleus. Again, momentum before collision is equal to momentum after collision. This is an important principle, as I will illustrate in the coming few minutes. You will see the power of this principle in solving problems. So, before collision, objects with their own masses will be moving with their own velocities. Like here, you have this object mass m1 moving with this velocity, v1 initial. This is the second object, m2, moving with its own velocity, v2 initial. They collide. After the collision, this guy bounces back, v1 final, and this guy bounces back in this direction, v2 final. So the momentum before collision must be equal to the momentum after collision. This is what we mean by the conservation of momentum principle. Okay? So the change in momentum is equal to the impulse, which is F delta T. Okay? This is how we calculate the change in momentum. F delta T here is positive, F delta T here is negative. If you add them, it is 0. If you add for an isolated system, the change in the impulse for the two colliding objects will add up, so you are talking 0. No change in the total momentum for the system. Okay? So now, when we apply the conservation of momentum principle, we can write equations, and as we know, equations allow us to solve for the unknown quantities. Usually you will be given some of these variables, and you will be asked to determine the other variables using the conservation of momentum principle. Okay? So here m1 v1 initial plus m2 v2 initials, this is the momentum before collision, equals m1 v1 final plus m2 v2 final. This is the momentum after collision. This is the meaning of momentum is conserved. And by the way, momentum is always conserved in collisions, while kinetic energy or energy may not be conserved. Energy may be conserved in elastic collision only, but in other form of collisions, it's not conserved, while momentum is always conserved. Okay? The other remark, you are talking here about the vector equation, which means you may have to deal with x components and y components. When you jump, the center of mass was at rest. So when you jump, the center of mass is moving up now with some velocity. So you may say, well, is this a violation for the conservation of momentum principle? How come? After the jump, there is a momentum. Before the jump, there was no momentum. So are we violating the conservation of momentum principle? The answer, of course, no, we are not violating anything. Because as a result of this action, of this jump, Earth received an opposite momentum in the opposite direction. But because the mass of Earth is so huge compared to the mass of the man, you will not feel the effect, you will not feel the motion, the velocity there. Okay? But if you take the system of man and Earth as an isolated system to apply the conservation of momentum principle, yes, momentum is always conserved. Keep this in mind. Momentum is always conserved, no exception. A boy standing at one end of a floating raft that is stationary relative to the shore walks to the opposite end of the raft, away from the shore. As a consequence, the raft, we have these options: remains stationary, moves away from the shore, moves toward the shore. Any suggestion? We need to apply the conservation of momentum. So the system, the isolated system in this case, is composed of the boy and the raft. So if the boy walks to the opposite end of the raft away from the shore, to conserve momentum, the raft should move toward the shore. Okay? It's like action-reaction pair of forces. So this way, as the boy moves away from the shore, the raft will move toward the shore in order to conserve momentum.